Radar systems development is complex, with many interconnected parameters and requirements. The analytical models for hardware and software components of these systems can be difficult to organize and explore. The Radar Designer app provides an easy-to-use interface for parameter input, design comparison, visualizations, and sharing of results. Let's walk through using the app for an airport radar design. We're going to design an X-band surveillance radar for detecting small targets. The radar should detect small manned aircraft up to 18 kilometers, small unmanned aircraft up to 8 kilometers, and maintain performance in heavy rain. On the left-hand side of the app, we have the input parameters for the radar, target, and environment. On the right-hand side, we have visualizations of the system and a table to compare the metrics to requirements. We'll start by adjusting the max range constraint, then input our threshold and objective requirements. The desired performance of the system is defined by the objective requirement, but the system is considered to have an acceptable performance if threshold is met. The manned aircraft is a swirling one target with radar cross-section of 1 meter squared. Now we can set our radar parameters. The frequency and peak power are set to values in the design specification, and the pulse bandwidth is adjusted to meet the range resolution requirements, and the pulse width is set to achieve high enough available SNR at the maximum range. The azimuth and elevation antenna beam width are set to 2 and 6 degrees respectively to meet the azimuth and elevation accuracy requirements. Scan mode is set to mechanical to give 360-degree coverage and azimuth. Including scanning in the analysis adds the beam shape loss and beam dwell factor to the link budget. The number of coherently integrated pulses is selected to satisfy the objective detectability with the swirling one case target and 1e-6 probability of false alarm. We account for losses due to pulse eclipsing and add this to the budget analysis. After these adjustments, the metrics and requirements table shows that this design satisfies the specification for small manned aircraft with RCS of 1 meter squared or larger. The specification states that the radar under design must maintain the required detection performance and the measurement accuracy in heavy rain. To include the path loss due to precipitation in the analysis, we set precipitation type to rain in the precipitation section of the environment panel. We then choose the ITU model and set the ranges such that 16 mm/h range is present in all ranges of interest. Now the metrics and requirements table and the SNR versus range plot show that the probability of detection at the maximum range is much lower than the required 0.9. We'll have to make adjustments to the design, so let's make a duplicate of this design just to compare the performance before and after. The probability of detection can be improved by either increasing the SNR available at the receiver or by decreasing the SNR required to make a detection. The latter approach might be more attractive in practice since decreasing the detectability factor can be accomplished through signal processing techniques that do not require making changes in the hardware. The detectability factor can be decreased by integrating more pulses. However, target RCS fluctuation usually imposes a limit on the amount of pulses that can be coherently integrated. A possible solution to integrating more pulses while addressing the problem of the RCS fluctuation is the M of n integration over multiple coherent processing intervals. Navigating to the radar panel and setting the number of CPIs in the detection and tracking section to 3 and the number of CPIs with the detection to 2 increases the resulting probability of detection. Although the probability of detection is still below the specified objective value, it meets the threshold requirement. This means that the system has an acceptable detection performance in heavy rain. Similarly, the range, azimuth, and elevation accuracies clear the threshold requirement, but are below their respective objective values. To verify this radar design will have satisfactory performance when the target is a small UAS, we can change the target RCS and maximum range constraint. The SNR versus range plot shows that the available SNR for this design is above the objective detectability line at 8 kilometers. We successfully designed a radar that can meet our requirements. We can share these results by automatically generating MATLAB scripts that recreate the plots and requirements and metrics table. These results can be shared and opened in spreadsheet software. For more information on our radar design capabilities, please visit our documentation.